In this video, we start talking about the fundamental theorem of calculus. So what I'd like to do is go over some of these formulas and understand why they work. This first one is the fundamental theorem of calculus, part 1 or part 2. I know there's two parts. The second part is down here, and then this one discusses derivatives. So we'll go through each one of these separately, and I want to explain what they mean, why they work. So let's start with this first one. This is the definite integral with constant limits of integration. A and B are constants, actual numbers. This f prime of x piece, and I put f prime of x there, but I could have put f of x. It doesn't really matter what goes there, but I wanted to remind you that when you integrate something, it's technically a derivative that you're integrating, and then the answer that you're getting is the original function, the f of x function. So if you have an indefinite integral and you integrate that, indefinite means that there are no numbers here or here. It's indefinite means there's no limits a and b. When you integrate that, your answer is the position function. It's the original, and then you have to add the constant of integration there because we don't have a location exact for it. Like for example, let's say we start out with f of x equals x squared plus 2. If you take the derivative of that, it's 2x. Well, what if it's x squared plus 20? The derivative of that is still 2x. What if it's 200 here? The derivative of that is still 2x. So when you integrate the derivative, it would look like this. You would have to say that it's going to be x squared plus c, because we don't really know what number might have been added, what constant might have been there. Could be a 0 for all we know. So anyway, this is the fundamental theorem of calculus. When you integrate a function, the answer that you're getting is the position. You're going backwards now. So in the first semester of this course, you learn about the derivative. You learn about starting with an f of x and then finishing with a derivative. In this case, we're now working the other direction, and we have a derivative, and we're integrating, and we end up with the f of x. It's going reverse now. Okay, so let's talk about this formula. Let me get off this page. It's getting a little busy. Okay, so the fundamental theorem of calculus is basically saying that if you integrate a function with constant limits of integration, remember what this means. This means area under a curve. It's the area under the velocity curve. It's actually equal to the function at each of these points. So when you integrate the derivative and get this f of x function, when you have constant limits of integration, which is a and b, you can get rid of this, and you're actually taking points off of this graph and subtracting them. You're taking the point when x equals b, whatever it is. In this case, it could be any number, and you're subtracting it from when x equals a, plugging it into the function. So the area under the derivative curve is the same thing as taking points and subtracting them from the original position curve. Pretty crazy. Let me show you an example. Let's say we have the integral from 0 to 1 of x dx. What this means in English is the area under the curve of y equals x. And it's on the interval from 0 to 1. So y equals x is a line, slope of 1, crosses through the origin. So really, you don't even need calculus for this. You can just find the area of a triangle using 1/2 base times height, and you end up with 1/2 times 1 times 1 here. So the area underneath that curve is 1/2. Okay, now remember, that is the velocity equation. That's the derivative. Y equals x is technically the derivative, and we found the area under the derivative curve, because that's technically what this integral means, equals 1/2. Okay, let's move on. Let's use some calculus to integrate. This would be the power rule, which this is to the first power. The formula is n plus 1 divided by n plus 1 here. X to the power of n plus 1 divided by n plus 1. So if this is a 1 here, now it's x squared, and then you're dividing by 2. So you could say x squared over 2. I personally like to make the 2 dividing by 2 a fraction, just so it looks, that's just the way I like it. Okay. Anyway, so now this is the position function. This is the graph of that function. This is our f of x. So f of x is 1/2 x squared. And if you think about it, if you take the derivative of that, it better be x, because that's what this is saying. So if you use the power rule on that, you end up with 1/2 times 2, and then 2 minus 1. So it does equal. This is the derivative. This is the position. So this is f prime, this is f. So now, what the fundamental theorem of calculus is saying is that if you find the area under the derivative curve, it's the same thing as taking points off of the position curve and subtracting them. And the points come from the limits of integration. So if we take f of 1 and f of 0 and subtract them, here's f of 1 right here, which will be 1/2 and then times 1 squared minus 1/2 times 0 squared. This is b, this is a. The formula is f of b minus f of a. Do the work right here and simplify, you end up with 1/2. It's the same thing as the area under the derivative curve. It's pretty crazy, actually, how that works. So sometimes you're given situations where you're not given actual functions to integrate. You might be given a table of points, and you just have to know that when you're integrating a derivative, it's the same thing as taking points off of its position function and subtracting, and it would be the points here based on whatever the limits of integration are. Okay, that was the first one. Here's the next one. Oh, I'm sorry, let's do an example first. My bad. I was ready to move on. Okay, so let's say we have, given that the antiderivative of f of x is 2 to the x power. Let me read that again. I'm saying it wrong. Given that the antiderivative of f of x equals 2 to the x power is this one, this is the antiderivative. Antiderivative is what you get after you integrate. So technically, this is the derivative, and then this is the position. The antiderivative is the answer after you integrate. So they give you the answer already. And notice that it's plus c. So, they're saying that this is the derivative right here. And if you integrate it, you would get this. And remember that you would add c. So it's the same thing as doing this without the limits of integration. So when you don't have anything here or here, you have to remember to add c, because you just don't know if there was a constant there. And again, it was that example I gave you. Let's just say we have x squared plus 4 this time. Well, the derivative of that is 2x plus 0. If it's 40, it's still 2x plus 0, because the derivative of this constant is 0. So the constant just kind of gets lost when you work backwards. So that's why when you don't have anything here or here, when you don't have, it's called an indefinite integral, when you don't have an a or a b here, anytime you do that, you have to add c. So they're giving you that here. They're telling you that if you integrated this equation, your antiderivative or your position function would be this equation here. So now they're asking you to evaluate the definite integral from 0 to 3. So that means there's no more c anymore. We don't have to add this anymore, but now we have to do that f of b minus f of a formula. So let's do that. So they give us this. They tell us that this is the integrand. This is the position function, which is the antiderivative. And now if we're going to use 0 and 3 as our a and b, we don't have to include that c anymore. So it looks like this now, or you can use like a little bracket thing. Either way, it's just a little formula, a little symbol that shows that you're getting ready to plug in a 3 and a 0 and subtract them. It always goes the bigger number first. Plug in the 3, and then plug in the 0 and subtract them. So it looks like this: 2 to the third power over the natural log of 2 and 2 to the 0 power over the natural log of 2. Now you can just simplify this. It's just algebra at this point. 2 cubed is 8 and 2 to the 0 power is 1. Those have common denominators. So we have 7 over the natural log of 2. That's an icky number. We can just leave it like that. Okay, let's move on to the next theorem. Now this is the derivative of a definite integral equals 0, where a and b are constants. So here's a definite integral, and we're taking the derivative of that, and it's saying that it equals 0. And here's why. Let's consider this integral again, from 0 to 1 of x. This was that triangle that we did a minute ago. Remember what a definite integral means. It means that this is the area under a curve. So if it's area, it's going to be a numerical value. So the derivative of this is the same thing as the derivative of 1/2, which is going to be 0. Anytime you take the derivative of a numerical value, you're going to get 0. An integral with constant limits of integration, I say constant because a and b have to be constants, it's equal to the area under a curve. This is always numerical. So then the derivative of this integral will always be 0 because the derivative of a constant or the derivative of a number always 0. That one's pretty straightforward. The next one adds on to this. It's the same exact thing, derivative of an integral, but now this case, a and b are not there. It's actually a constant. C is a constant in this case, but g of x, this is a function of x. This is where you have like an x in the limit of integration, an x squared, a 2x, some kind of function of x. It's usually a red flag when you see this. And what you do is you take this function, and this is when you're finding the derivative. You take this function and you literally plug it in to the variables of the integrand. And then you remember to multiply by the derivative of that function. So let's do an example. Let's pretend for a second that you don't know this formula. Okay, so here's a function. I'm going to call it a of x because this represents area. Let's integrate this. Let's use calculus, and we'll get t cubed over 3 with the power rule and then times it by 3. So those 3's are going to cancel. And now the fundamental theorem would state that we stick this in here and this in there and subtract them. So let's do that. So you'll have x squared raised to the third power minus 0 raised to the third power. Simplify that, you get x to the sixth power. Now that's not the derivative, that's just the integral. That's just this piece of it. Okay, so now let's take the derivative of that. A prime with derivative of x to the sixth power would be 6x to the fifth power. Okay, that's straightforward enough, but sometimes you get an antiderivative or an integrand here that you can't do by hand. So let's use this formula that I'm showing you up here. This is a shortcut, so much easier. So what you do is take this, plug it right in to that t. So it's going to be x squared raised to the second power. So 3 times x squared raised to the second power, and then times the derivative of the x squared. Don't forget that part, don't forget that part, don't forget it, don't forget it. So 3x squared squared times the derivative of x squared. Simplify this, you get 3x to the fourth times 2x, 6x to the fifth. It's the exact same thing in like 3 steps. So let's do a quick example of this. Given that f of x equals this integral, find the derivative of this integral. Notice that you have an x in the limit of integration. Huge red flag, huge. When you see an x in the limit of integration, you're going to be taking the derivative. You're literally going to be plugging it in right into that t. So you're going to do 3x and square it. And then, don't forget, multiply by the derivative of that 3x. Simplify this, that's 3x times itself. Done. That's all you do for those. When you have to take the derivative of an integral with an x as a limit of integration, you plug in and then multiply by the derivative of that limit of integration. Done.